So we started this whole thing about the coordination compounds with the promise that we were going to actually look also on the effect on the metal, on whatever is on the center, right? So if we consider fundamentally transition metals, remember that this thing is also valid, but needs to be adapted for rare earths and stuff like that. So far, we've been talking about what bonds to them, but then the question would be what happens to them. So in this section, we are going to see all of the effects of the coordination on the metal and what are the effects that are then geometry dependent that follow that. So the first concept that comes from this is that inherently, when we look at transition metal complexes, we're looking at something that is using d orbitals to bond. We derived a series of electron configurations in our previous video, and every time we landed on something that had valence with d electrons. It could be any period of d electrons, 3D, 4D, 5D, early stage, late stage, but they're still d orbitals. So this is a shell that is characterized by 5 orbitals. All of these orbitals tend to be highly directional. So unlike the s orbital that is a sphere, or the p orbitals that have this x, y, and z type of directionality, the angular momentum of the orbitals here allows them to have these very complex shapes that can go in multiple directions at the same time while retaining, technically speaking, the same energy. So the metals arrive with this cluster of orbitals. So when you are interacting with the valence of a transition metal, you're interacting with all of this at the same time. So highly directional, multiple directions, some very marked, others degenerate and things like that. But in general, all of these are at the same energy, so degenerate in energy to begin with. And they are more localized than the S and the P, so they belong more to the metal. They do not hybridize. So in a first approximation, we must consider that we cannot make a hybrid of the orbitals. This is not physical. We're not going to do it. We are not going to use valence bond theory, but we must still know how the interaction of the ligand is influencing these orbitals energetically, because something must be happening. We know the complexes are there and are formed. So what happens? A general theory that is applied here is what is called the crystal field theory. So this is a broader theory. We will go in more advanced theories in next lectures, but the fundamental idea is that if you have an isolated atom, then we know that you have these d orbitals that come with it. If the atom is isolated, the orbitals will be degenerate, all at the same energy, at the energy that is accounted for them from quantum mechanics. If you put this metal in a spherical potential, so you're going to make it feel an even potential of charges around it, this thing is going to lift evenly all of the energies of all of the orbitals at the same time, because the potential is spherical. All the orbitals are going to feel the potential exactly in the same way. However, in a complex, we know that the ligands don't come from every direction isotropically. They do not come from a sphere. They come with a very precise directionality of interaction that is given from the geometry. So you are going to have a very precise point in which the electrostatic interaction with the other thing that is bringing the electrons is triggered, and other directions where there is nothing. So these orbitals will be further influenced. They will be higher in energy than they would be if they were to be feeling nothing, but they cannot possibly feel this effect evenly. This means that the energy of the d orbital is not going to be degenerate anymore. They will split one way or another. Some will feel this energy more, some will feel this electrostatic potential less. The orbital arrangement will split, and this will depend on where are the ligands approaching from. So this is what is called the crystal field theory. So if we want to apply to a very symmetrical geometry to begin with, one of the most symmetrical options you can have, actually the most symmetrical among the things that are reasonable to find in transition metal complexes, is the octahedral geometry. So the octahedral geometry, in comparison to a reference of axis that you can give yourself, that usually by default tends to put the x-axis going up in the page, will have ligands pointing in different directions, but they fundamentally point at the very least on this axis if you align your center of mass, so what would be your metal, here on the origin. So the ligand is coming from X, from Y, from Z, and they come directly. This means that if you consider what the metal inside is going to bring, you're going to bring all 5 of the d orbitals into this field. This is now your crystal field. You have one orbital that points directly in the Z direction. This is the Z square. You have another orbital that points directly both in the X and the Y, because it is the orbital that lies on the axis with both of the components at the same time. And this will be the X square minus Y square. The other orbitals are all the combination of orbitals of all of the axes. So XY, which is in the bisecting of the axis, YZ, and XZ. So you can see that all of them are going midway through in the axis and flipping with the components. So the one that point directly in the direction where these conceptual negative charges are coming towards them are going to be higher in energy. They will rise energetically because they point towards the ligand. Whereas these other 3 that are left over are not pointing directly towards a ligand, so they're going to be lower in energy. You can see that this becomes a split. This split, given this is an octahedral arrangement, is an energy split of an octahedral field, which we will call delta O. And the difference here, you can see that in comparison to the center of gravity, so the same height where the original d orbitals were energetically, this rise and fall is not even because you have 3 at the bottom, 2 at the top. So you have this 3/5, 2/5 thing, or 0.6, 0.4. Note that these things, you can label the orbital, and you should label the orbital because this is not always the same. This thing comes with these labels over here, this EG, T2G. These are symmetry labels. They describe the shape of these orbitals in an octahedral field. We are going to see more of what exactly do they mean in lecture 4. So it will come, but for now, know that in an octahedral field, you have these ones that are up here that are labeled EG, and the XY, XZ, and YZ that are T2G type of orbital. Yeah. So the other option, if we go slightly down in symmetry, would be to use a tetrahedral arrangement. Now, a tetrahedron, you could consider it as something that is encased in a cube. So in every cube, if you then put 2 corners at the top and the opposite 2 corners at the bottom, in comparison to the center, this is exactly what a tetrahedron is. If you encase your 5d orbitals here, you can now notice that, first of all, there is nothing really that points directly in the direction of multiple ligands at the same time if the charges are coming in a certain direction. But considering the amount of interaction, the dx square, sorry for the different labels here, but x square or z square will be the same stuff. So dx square and the z square, x square minus y square will be actually furthest away from the interaction of the ligand, unlike the octahedral field. Whereas every other orbital, by having this bisecting line of partial arrangement, will have a partial level of interaction. So it is a flipped version of what the octahedral crystal field was. Now the three bisecting the orbitals are the ones that point higher, and instead the two x square minus y square and z square end up having the least interaction, so they go lower in energy. This is again not a 50-50 split. It's still a 0.6, 0.4, but again, it's flipped. You have 3 at the top, 2 at the bottom. The difference between these levels is what is called the tetrahedral crystal field. So the delta T is the thing that gives you the difference in energy, how much they split. Once again, these have an symmetry label, but given that the symmetry of an octahedron is not the symmetry of a tetrahedron, remember that these are T2 at the top, E at the bottom, instead of EG at the top, T2G at the bottom. So this is all an energetic type of consideration. If we compare these two key geometry against each other, we have the core of the crystal field theory. So the difference in splitting is given by the level of interaction. So, and this is also tells you in which order do you end up then filling the orbitals, because since they're not degenerate anymore, you will fill first the one that are going to have the lower energy. When you compare them to each other, so you can see the split with all the labels, the axis in energy, and the fact that this thing is delta O as the highest possible one is 10 dq. dq is a standard way to label this amount of energy. It's a standard crystal field denomination. You can take it as granted. If you want to see a full derivation of what dq is, please go onto this link. This is for your own interest if you're very mathematically inclined. Otherwise, you know that this is a quantum mechanically derived split. So when you define dq, you just refer to all the constants already calculated, then you can just use it as this is your 10 dq. You can fraction it depending on where you occupying things. Note that a feature that is very important to highlight immediately is that it doesn't matter what is going on in terms of what metal, what ligand, what whatever. The tetrahedral configuration has a split that is always smaller than the one of the octahedral because of this alignment and misalignment of ligands. So this split is always going to be bigger. How bigger? Actually, the tetrahedral crystal field, so this delta T, is always 4/9 of the delta O. It's always smaller. This is something that we need to take into account when we need to know how to fill the orbitals. So you have two options. First of all, you always have to follow the Pauli principle, so you can only have two different spins, and the Hahn rule still applies. But the point of the Hahn rule of like normally when you have 5d orbitals at the same time, you will just fill all of them and then start pairing. Here, the question of do you do 1, 2, 3, 4, 5, or do you do 1, 2, 3, 4, 5 depends on the entity of this jump. If jumping to the higher level is easier than pairing, because pairing a spin by flipping the spin of an electron will cause you some cost, then if you prefer jumping rather than pairing, then you end up in a high spin configuration. Everything goes in the highest possible occupation before you start pairing, right? If instead, pairing is easier than jumping. So this gap is more difficult to cross than pairing the energy. Then you find yourself in a low spin configuration. So you prefer pairing over than occupying how many things as humanly possible. Now, we know that a tetrahedral is always smaller than an octahedron. So this jump is always going to be tiny, which means tetrahedral complexes are all high spin. You don't get the low spin configuration. There is no reason to cram all the electrons here if they can just see the one available above. Everything else, in general, the entity of this delta, and be the delta T or the delta O, the entity of this jump depends on the chemistry. So first of all, oxidation state of the metal. A metal with higher oxidation state is going to have a higher delta. This comes with, since this is an interaction with whatever is coming in, the oxidation state also modifies the electron cloud. Given the feature of the electron cloud, you need to remember that the group, as you progress in N, will affect the energies. So the nature of the metal will make so that this gap changes. So the gap of a 5D is going to be bigger than a 4D, which is going to be bigger than a 3D. This goes in a sequence of N. And different ligands will exert a different strength. So the interaction will be stronger or weaker, which will make this jump bigger or smaller. So you cannot consider all the ligands at the same time. But this we're going to see in lecture 3 as we go on a slightly more advanced version of this option. So if we say that the complex likes to be a complex, is because technically speaking, there must be an advantage from an energetic point of view in interacting. There must be something that is making the interaction profitable from the energetic point of view. So this profit is something that you can check with the crystal field stabilization energy, CFSE, which can be set up for both the octahedral configuration or the tetrahedral configuration. So this is balanced against how many electrons are filled in those orbitals. So if you're filling orbitals if you're filling electrons in an orbital that is already energetically higher, then this thing will go against the stabilization. If you're only filling orbitals that are energetically lower, then you're gaining energy every time you pair something, in comparison to the case of no crystal field splitting. This means that the T2G filling of the octahedral is the one that brings the energy down, whereas the EG filling is the one that brings the energy up. It is exactly inverse. Sorry, this is supposed to be a 4. I will correct it. Is exactly the opposite in the tetrahedral field. So you switch these things around because of the stabilization. And you put the number of electrons. Obviously, if you have no electrons in, then whatever. Can we have some examples of this? Of course. So if you consider, again, same example that we used before, the hexachinoferrate 3-. This is an high-spin complex. And your configuration here, as we derived before, is D5, because this is an iron 3+ type of ion. So given the 6 ligands, this is going to be an octahedron. So we're going to have 3 T2G orbitals and 2 EG orbitals rising up. We have 5d electrons to fill. We say this is a high spin complex, so they must be filled like this. So you go in sequence, you go higher, you have nothing else to pair, so you don't go back down again. Because you have 5 orbitals, you filled all of them, it's fine. If we calculate the crystal field stabilization energy, this actually goes to 0. So the complex is not destabilized, it's not stabilized, it's perfectly fine how it is, which is also a reason why you might like to not have less than 6 coordination. If we do this with the hexamino cobaltate, If we say that this is a low-spin complex, which can happen actually, then we're saying that we want to pair the electrons rather than go higher. As we derived before, the cobalt here is in a 3+ oxidation state, which makes this compound a D6 type of configuration. So it's a 3D6 metal. You need to place 6 electrons, but you need to place 6 electrons with a preference to pairing them rather than rising. So this means that you're going to use all of the 3 T2G orbitals, 3, and then the other 3 in the other direction. There is nothing in the upper level. If you do the calculation, this gives you the stabilization. So you go negative in energy, 2.4 delta O, because you put electrons, all of the electrons, in all of the stabilized orbitals. Now, the stability of something might very highly depend on what did you put in. And one of the theorems that was associated with crystal field was that given that we derived the cornerstones of crystal field as tetrahedral, octahedral as type of geometry, the occupancy can give rise to different energetic scenarios. So the Jahn-Teller theorem is the one that dictates that the stability of a complex and the degeneracy of its level are not compatible at the same time unless you have a molecule that is linear, which was later evolved into the idea that any system that is not linear, in which you end up having energetic degeneracy in the orbitals that could potentially be removed, will undergo a removal of the degeneracy. So if you have it, then you will try to take it away. This can be done since you got the crystal field by geometry. The distortion of the geometry is the thing that can give you the loss of degeneracy. So what do we mean with degeneracy in this system? So if we use the octahedron as the example, then we have 3 of these that are at the same energy, 2 of these that are at the same energy. It's not 5, but it's still not completely separated. If you distort the geometry, so instead of having all bonds equal, you elongate on the z direction, then suddenly you're going to have a split of things. So you split up. So if you, depending on, do you elongate on the z or do you elongate the basis, so you compress on the z, then you split the option of what do you have. Since not all the bonds are equal anymore, you cannot fill evenly both z square and the base. You need to split the orbitals. You can see that this split is tiny, but it is still present. And inevitably, if you split this, then also the lower one are going to split. So once again, here, these two that have a z component will go slightly up, but this one that have an xy component, in the same way, this one is going down, this one is going down. Same thing on the other side. This one that has an xy component, if this one is going up, then this one is going up. This is all by geometric distortion. So the molecule is slightly changing shape so that it could potentially change the energetic gain of being bonded. Note that there are some electron configuration that by their configuration do not allow, in any case or shape or form, a Jahn-Teller distortion. So if this is a Jahn-Teller distortion, but you have a D10, there is no reason to undergo a distortion because a D10 will fill all of this evenly. So the even filling of all of the orbitals at the same time would mean that distorting the geometry will be a zero-sum game. Whatever you gain, you lose. Whatever you lose, you gain, so you don't want to distort. If instead you start to have levels that are emptier, then it will make sense to do the filling. Once again, can we have an example? So if we use our copper X aqua 2 plus type of thing, our copper 2 is in a D9 type of electron configuration. A D9 type of electron configuration means that the moment we set up the crystal field, you end up with one that is not full. You have 5 orbitals, each of them can accommodate a total of 10 electrons, but you have 9 electrons. So you could have this filling, or you could have this filling. And I know you might be tempted to tell me, oh, but this is exactly the same. This is exactly the same because these 2 orbitals are at the same energy level. So you are giving an option to the complex to have this spin flipping from one to the other. So am I in dz square? Am I in dx minus y? Am I in d square minus y square? These are 2 options, and the system could do both at the same time because energetically they are the same. This is exactly the case in which the Jahn-Teller theorem comes to fruition. The stability of the system and the degeneracy of the level don't go at the same time. The system will try its best to remove the degeneracy. And what is the best of the system to remove the degeneracy? We could split. So if this is our arrangement, and we do an elongation, then we end up with less interaction on the Z, more interaction on the X. So we split this off, right? So now, instead of finding yourself with this option, you now have one lower that gets completely filled and one higher that is singly occupied. This doesn't have anything else to do. Everything else is filled. So the one that could have the option has the option removed. So how do we quantify this stabilization energy? So first of all, if you look at the octahedral arrangement, we could calculate the crystal field stabilization energy from octahedral point of view, which is minus 0.6 delta O. To calculate the gain that you will get, if you get any gain from a Jahn-Teller distortion, then you need to consider the energy of the distorted configuration minus the one of the octahedral configuration. So this whole business, but you can look up what are all the parameters, right? Because you have the Feuder splitting, so you have a Feuder gain, a Feuder loss, a Feuder gain, a Feuder loss, once again balanced against how many orbitals are you splitting. So this is delta 1 half, but this is delta 2 third, because you have 3 orbitals that you need to Feuder split. So this is done exactly in the same way as you will do this, but then you count with the split, right? And you don't consider the energy of the octahedral because you already calculated this one, right? So you need to go with all the these, because you have 2 electrons here, 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 here, you only have 1 electron. So you can already imagine that this one should cancel out completely. This one will not cancel out completely. So this is the deviation from if this is what you had before, then there is a Feuder gain. So you could have already guessed that the difference between the octahedral and the distorted version is this half thing. So the half split that you gain is the reason why you would like to have the complex in Jahn-Teller distortion configuration. So this is how it actually looks. So 2 long axial bonds, if you consider that this axis has this square, depending on how you put your axis, is either one or the other. Then this one is elongating. Then this is elongating. This is compressing. The one that is compressing is feeling more of the electrostatic energy. And this one is the actual experimentally determined arrangement with the experimentally determined bond length. You can see that the effect is incredibly tiny. We're talking about 0.45 angstrom, but detectable, and it is impactful in energy. Some additional notes on crystal field stabilization and the Jahn-Teller distortion. Some of the calculations that you might find around will actually take into account the pairing energy, because the pairing energy is the one that makes a difference between high spin, low spin, or tetrahedral and octahedral. Sometimes you might prefer one or the other because being forced to do the pairing will take you so much energy that you don't want to do it. The calculations are fundamentally accurate, but be careful of remembering this pairing, which is usually noted as P, because some more advanced calculations might note it down as something that you need to take into account, especially if you're trying to figure out if something will be stable or not stable and you're not quite sure. For the Jahn-Teller distortion, from an experimental point of view, given how things are aligned in the crystal field of an octahedron, the actual observation of a Jahn-Teller distortion can only be observed if the orbital you're removing the degeneracy at is one of the EG. If you are distorting in the T2G orbital, which is something that you could consider if you have a lower electron configuration in comparison to D9, this is usually not observed. This is because the energetic of the influence of removing something or like putting something further away that is pointing directly at the ligand is massive. We saw before, it's a half in comparison to a third. It will make a lot of difference. In general, Z out elongation is preferred because dz square as an orbital has these 2 lobes instead of 4 lobes. So you need to do the least movement to gain the most energy, which is what the system will prefer. It could happen, though, that your Z in or Z out, so compressing like this, elongating like this, so either you squish or you elongate, are energetically equivalent. This is a temperature-dependent effect. You could have it more prominent at higher temperature, more prominent, stuff like that. This is what is called dynamic Jahn-Teller distortion. So most of the Jahn-Teller distortions that you're going to see are going to be static. So once it forms, that is the configuration. But your complex might oscillate between Z in, Z out, Z in, Z out, if the system allows for dynamic Jahn-Teller distortion. So it's 2 configurations at the same time, exactly like the Berry pseudo rotation could give you 2 conformations at the same time. Remember that we only covered tetrahedral and octahedral as the most fundamental arrangement, but there are other geometries, and we've seen complexes that follow a different geometry. So for the right metal in the right electronic configuration and the right ligand, some of these geometries might be preferred actually in comparison to tetrahedral or octahedral. The energetic considerations to be able to arrange a crystal field stabilization energy diagram are exactly the same. And these are the ones that you should use to figure out what are the arrangements in this type of geometry that are not going to be octahedral, they're not going to be tetrahedral, but one way or another, you need to orient your orbitals. We discussed now what happens on the metal. So you clearly had this inherent removal of degeneration because you are pointing in a specific way. So you can consider the metal to be coming only with the atomic orbital because they don't hybridize with anything else, and they should not hybridize with themselves for sure. But at this point, you will still have a bit of a gap Like we know what this is doing in terms of crystal field if we considered all of these ligands to come as hard spheres, but we can already see even in an arrangement like this that this thing is different from this one. And this we know should come and bond with molecular orbitals. Whereas we say that this one, if we consider it with a compressed conceptualized model of hard charges coming from a specific geometry, will split the d orbital one way or another. There is one thing that we are still missing, which is the nature of the bond. How do they bond together? How is this thing held together? Because the crystal field stabilization energy sort of assumes an electrostatic interaction, but this might not necessarily be true. So in the same way, we wanted the true version of a bond in a ligand with molecular orbitals. It will be time to then step up and check the nature of the interaction, the nature of the bond between a metal and a ligand. But this we will do in lecture 3. These are your learning objectives for week 2. And I will see you in lecture 3 with all the additional material that will come through the lecture. Thank you very much, and I'll see you soon.